Okay. Thank you very much for the invitation, and thank you all for being here. So today I'll be talking to you about my research on multi-contact locomanipulation, focusing mainly on addressing some of the challenges in whole body planning and control design. So let me start by highlighting some of the intricacies in locomanipulation planning by looking at a seemingly simple example of a legged mobile manipulator opening and traversing a door. So solving such a task would require the robot to fulfill a multitude of sub-goals. For example, it should apply the proper forces to open the door while simultaneously maintaining balance and avoiding collisions with itself and its surroundings. It should also be able to decide where, when, and with which limb it wants to interact with the object. And all this should be done in a smooth and coordinated manner while satisfying various system-related constraints. Now, trying to manually handcraft the entire behavior while jointly handling all of these considerations can be a very difficult and time-consuming process. So we need a more principled approach that systematically and holistically addresses all of these challenges. And as you all know, many of the elements listed here can be naturally incorporated into the optimal control framework. The problem is that the gradient-based algorithms used in optimal control are unable to optimize through contact transitions. And that is because they inherently rely on smooth functions in their formulation, whereas contact dynamics exhibit non-smooth and discontinuous phenomena at contact switching events. So how can we formally address that? In its most general form, multi-contact planning can be mathematically cast as a mixed integer optimal control problem, where this newly introduced variable z is a discrete variable that encodes different contact modes. Now, existing methods used to solve this problem rely on combinatorial search techniques such as branch and bound, which do not exploit any special structure in the problem. And this makes them computationally intractable due to their exponential complexity with respect to the number of discrete variables and the number of time steps. So the main objective of our research has been to investigate and propose ways of relaxing this problem in order to make it solvable. And just to give you a general overview of how this talk will be structured. In the first part, I will start with a common approach that simplifies multi-contact planning into an optimal control problem for switch systems. And the way this is done is by assuming contact transitions are manually specified, for example, in the form of a gate pattern or a manipulation schedule. And the focus here was to unify the treatment of dynamic locomotion and manipulation into a single MPC framework. And since this is a relatively old paper, I won't spend too much time on it, but it's still important to motivate and give you the full picture of the next work. Now, to get rid of these manually designed contact schedules, we look into hybrid search as a way of automatically generating holistic behaviors. These algorithms combine different planning techniques to discover both continuous trajectories and discrete sequences like contact switches. And in this central part of my talk, I'll introduce a new perspective that models multi-contact locomanipulation as a task and motion planning problem. I will then show how this leads to a bi-level optimization, which can be solved efficiently with a hybrid search technique. And this planner enabled our robot to solve complex and long horizon tasks like traversing spring-loaded doors and manipulating heavy dishwashers. In this last work, we focus on the controller element, aiming to robustify the behavior execution phase. So we resort to demonstration-guided reinforcement learning as a way of systematically training robust locomanipulation policies. And the key idea here was to formulate a unified Markov decision process that leverages high-fidelity demonstrations given by our previous planner. And this gave us policies capable of robustly executing different behaviors while withstanding external disturbances and modeling mismatches. Okay, so start with the first work. When it comes to motion planning for multi-limbed floating-based systems like humanoids and quadrupeds, many of the early achievements in the field can be attributed to the modular design approach. It essentially decomposes the planner into simpler modules where, for example, One is responsible for generating center of mass trajectories, another one for swing-like trajectories, and a third one for pure manipulation planning. The problem with this approach is that it ignores the interplay between these different components, leading to limited domains of operation. So instead, we focused on generating holistic solutions by combining locomotion and manipulation planning into a single framework. And we do that in a way that tries to capture dominant dynamic effects while keeping our planner real-time capable. At the core of our formulation is an optimal control problem tailored for switched systems. So the idea here is that time-dependent constraints can be systematically used to encode any predefined mode schedule. And this mode schedule is basically a mode sequence coupled with a set of switching times. We also rely on model predictive control as a way of generating stabilizing plans for our system by repeatedly solving this optimal control problem. And we also use a Riccati-based solver, which is generally favored in real-time control applications due to its efficiency. So briefly, let's look at the main components of this formulation, starting with the equations of motion. So the most accurate model one could use here is the robot's full rigid body dynamics. But as you all know, to achieve rates suitable for online replanning, it is common to extract a simplified model from the system's unactuated dynamics by relying on certain simplifying assumptions. So in our case, we went for a sufficiently accurate yet minimal representation given by the system's full centroidal dynamics and first-order kinematics. So the system state includes the centroidal momentum, the base pose, the joint positions, and the control inputs include the contact forces and the joint velocities. And because we're dealing with whole body manipulation problems, having a planner that is also aware of the dynamic couplings between the base and the object is very important for carrying out the task effectively. And the way we achieve that is by augmenting the object state and its corresponding dynamics to the robot model. And as mentioned earlier, we can use our reference mode schedules to define time-dependent contact constraints, and this is done by extracting a mode at each time, which in our case represents the set of closed contacts, and then using this mode to impose the corresponding constraints. For example, forces at open and effector contacts are set to 0, and closed contacts, which could be between a foot and the ground or a gripper and an object, should have 0 relative velocity. As for the inequalities, these are used to ensure that the feed forces remain inside their friction cones and that the system operational limits are not violated. They could also be used to enforce self-collision avoidance and environment collision avoidance by representing collision bodies with primitive geometric shapes. Okay, so let's see what can be achieved with our MPC framework at this point. So here you see the robot solving a reaching task, and you notice the torso clearly adapting its pose in coordination with the arms movement. And this highlights the importance of including the full kinematics in the planning phase to exploit this redundancy. And here you see the robot perform dynamic maneuvers like throwing a dumbbell or walking around while using the arm as a tail. And this highlights the planner's awareness of the couplings between the base, limbs, and the object. And in this final example, the robot is required to push or pull heavy spring-loaded doors, and the planner figures out the whole body motions and contact forces that solve the task, and it also manages to mitigate external disturbances, highlighting the importance of fast online replanning. Now, one limitation of this approach is that it still requires carefully crafted cost references and manipulation schedules, especially when dealing with complex long horizon tasks like traversing spring-loaded doors. So in our next work, we aim for a minimally guided approach that automatically discovers both whole body trajectories and the full manipulation schedule for various tasks. So what makes this problem difficult is that it encapsulates all of these technical challenges at once. So, for example, it involves planning in a hybrid search space where the task duration is unknown beforehand. And because we want a minimally guided approach, we avoid densely defined objectives and informative initial guesses. And this makes it highly prone to bad local minima. Now, there are no existing optimal control methods that can deal with these challenges in a principled way. So we consider a different paradigm, task and motion planning, or TAMP. In combined TAMP, reasoning about high-level task plans and low-level motion plans happens simultaneously. So the task planner generates a discrete sequence of state action pairs, while the motion planner computes continuous trajectories conditioned on this task plan. And to ensure that the discrete search does not grow exponentially with the size of the problem, task planners are often symbolic, resulting in fewer actions to choose from. So the main research question that we wanted to address here is how can we model multi-contact locomanipulation as a task and motion planning problem and solve it as such. So we start by assuming we are given a user-defined collection of end effector contacts and object contacts. And notice here that the object contacts are not necessarily points, but they could also include surfaces. And now from these, we can construct a symbolic state space that encodes all possible combinations of contact pairings between the robot and the object. For instance, this state indicates that the first 4 end effectors are open contacts, and the 5th end effector, so the gripper, is in a closed contact with the first object contact, so the door handle. As for the actions, a trivial definition gives a large search space, including all combinations of contact switches. And we would like to make this search space smaller, so we introduce a basic rule that greatly reduces the branching factor. We restrict each action to affect one end effector at a time. So such a rule gives us a compact representation for the symbolic actions, where the first element represents one of the end effectors, and the second one represents the object contact. So let's look at an example to understand how the transition map works. The first action here causes foot number 1 to establish a new contact with the front surface of the door, while the gripper maintains its previous contact with the handle. The second action causes the 5th end effector, so the gripper, to break contact with the handle. And this last action maintains the same contact state as before. So we can further reduce the branching factor by introducing additional pruning rules that are either generic or domain specific. For example, contact pairings that are not kinematically feasible can be immediately discarded. A non-prehensile foot cannot be paired with a prehensile object contact. And the number of feet being employed for manipulation should not cause the robot to be statically unstable. So now we can pose our planning problem as a hybrid bi-level optimization. The outer level would consist of an informed graph search over contact sequences, where the edges represent trajectories given by an inner level trajectory optimization. And the cost of each edge is determined by a penalty on contact switches plus the total cost of the optimal trajectory. Notice here that we consider the full plan to be divided into coarse intervals of mode invariant phases. And the reasoning behind this is that manipulation modes tend to remain constant over multiple consecutive time steps in a short horizon. And this causes mode switching to occur less frequently along the full horizon, reducing the number of decision variables even further. Now, to solve this problem, we use the sampling-based bi-level search that gradually builds a tree of mode invariant trajectories. So each color here represents a certain contact mode. Each node is characterized by its contact mode and reachable terminal state given by the trajectory. And the node extensions are divided into goal-directed and purely random extensions. And this strategy gives us a nice globalization property that encourages fast exploration and helps avoid bad local minima. We then apply a post-processing step to enhance the quality of the solution. So we use the discovered solution as an initial guess to warm start a single long horizon optimization. And in this case, we fix the underlying contact schedule. And this gives us smoother and lower cost solutions with higher feasibility, which facilitates transfer to the real system later on. Okay, so to demonstrate the planner's versatility, we conducted a series of simulation experiments on 2 object-centric tasks and 2 robot-centric tasks. The only thing we specify here is a sparse task description in the form of a goal region, along with a collection of end effector contacts and object affordances. And as a result, complex multi-contact behaviors emerge in less than a minute, which enabled our robot to manipulate a heavy dishwasher while exploiting a mixture of prehensile and non-prehensile interactions, manipulate a large valve while using multiple regrasps whenever necessary, traversing large movable obstacles, even when the arm is intentionally blocked by having it carry a load, and finally, traverse large articulated objects of different types, where interestingly you see different manipulation schedules emerge for the recoil door case versus the non-recoil door case. And some of these behaviors were also executed on the real system using this 2-layer tracking controller. So it consists of a whole body MPC planner that is similar to the one I explained earlier, and the whole body controller that simply tracks the MPC solutions. This structure greatly bridges the gap between offline behavior generation and online execution, and it gives us a task-agnostic way of transferring locomanipulation plans to the real system. Now, the hardware experiments showed our robot traversing spring-loaded pull doors with the independently generated plans. So here you see the robot using its foot to prevent the door from recoiling back as it switches the arm contact. So traversing a spring-loaded push door with plans exhibiting different manipulation schedules. So if you notice, the one on the left uses its front foot to hold the door as the gripper goes from the handle to a non-prehensile interaction. This doesn't happen in the other two. So opening a heavy dishwasher where the contact switch that you see here was necessary because of the arm's joint limits. And closing it, where you see the robot first using its foot to lift the dishwasher, making it then easier for the gripper to establish a non-prehensile contact with the front surface and allowing it to close the dishwasher. Now, the main limitation in this work is primarily connected to the task execution phase. So for example, here we deliberately make the robot fail at this task. And you can see that it manages to detect this failure and restart the motion. But this was only possible by hand engineering this recovery behavior into a state machine. Otherwise, the robot would have simply continued on executing the motion, resulting in a collision with the closed door. And basically, any large deviation from the nominal behavior at this point would lead to a similar failure. So in this last work, we tried to address this limitation by leveraging demonstrations generated by our planner to train a robust locomanipulation policy. And we did that using deep reinforcement learning. And the idea was to use a single nominal demonstration per task and use domain randomization to achieve the desired robustness. And the goal is to formulate a unified Markov decision process that works for multiple behaviors without any task-specific reward shaping or hyperparameter tuning. So one common way of tracking single demonstrations with RL has been to introduce a task phase variable that is blindly updated and used to query references from the start of the trajectory to the end of the trajectory. This is what we refer to here as the nominal formulation or the nominal phase dynamics. In our case, this included the observations that are a function of the robot and object tracking errors, their velocities, and the robot's end effector states. As for the rewards, these include simple quadratic terms that penalize deviations from the reference and try to regularize the motion. And this choice of observations and rewards is not unique, but it only captures the essence of a trajectory tracking MDP. Now, if we test the resulting policy on our simplest scenario, we observe that even when a disturbance is applied to the robot, as you can see here, it still manages to solve the task. On the other hand, it struggles to solve the more complex tasks, which include multiple contact switches. And the issue here is that even if the object reference is not being tracked anymore, the phase keeps on increasing blindly, causing the policy to execute the remaining part of the robot's motion and ignore the object references. So this motivates the need for a more complex phase dynamics that allows for adaptive phase updates. And the way we do that is by introducing phase dynamics that try to reflect the task level tracking accuracy. So we define this function in a way that makes it pause the motion for large deviations from the reference, or gradually approach the nominal rate as the tracking performance improves. And these resulting dynamics induced a sort of guiding effect during training, which is similar to that achieved in reward-driven curriculum learning. Now, in some cases, the robot may unexpectedly lose contact with the object, and the only way to recover and complete the task is to go to a previous phase. So to provide this flexibility, we restructured our policy network to output an additional residual action that can potentially speed up, slow down, or decrease the phase whenever necessary to complete the task. And finally, we add one extra reward term to the total nominal reward to encourage progress in the adaptive task phase. Okay, so you can see now that all resulting policies manage to successfully solve the tasks they were trained on. And this happens with an average success rate exceeding 90% for all 4 behaviors, even in the presence of external disturbances and mismatches in the object model. Here we highlight the importance of including the learnable residual action in the phase dynamics. You can see from the plots that without this component, the task phase is paused as soon as the robot loses contact with the handle. And the phase cannot be decreased anymore in a way to reestablish this contact and complete the motion. We also experimented with a multitask training setup where a single policy learns to execute all 4 behaviors. And this was done with a simple adaptation to our formulation where we included an extra observation in the form of a one-hot vector that encodes the desired task. And finally, achieving a reliable execution on the real system is still ongoing work at this point, but so far we managed to do a preliminary sim-to-real verification on one of our tasks. So from here, we see 2 potential areas of future research that build on our work. First, we note that the approach presented in the last work has an underlying assumption of full state feedback, so including the state of the robot and the object. So the first natural extension would be to relax this assumption by training a perceptive policy that incorporates extraceptive information. And we believe this can be achieved with a teacher-student training setup where a teacher has access to privileged information and the student learns to imitate the teacher's actions using information only from the robot's onboard sensing. Another interesting direction would be to replace the single demonstrations with a closed-loop planner that can continuously update these plans. For example, we can train a diffusion policy on a large Locomanipulation dataset generated by our planner, and then we can incorporate it as a high-level planner providing on-demand references to the lower-level RL policy. And finally, I'd like to thank my sponsors, my advisor Marco, and my collaborators at RSL, and thank you all for your attention. I'd be happy to take any questions.
Thank you very much. Thank you very much for the great presentation. Question time. Go ahead.
Hi, thanks for the great talk, very nice results. I was wondering, in your last part, the guided reinforcement learning, instead of having to deal with this phase variable which decides when to switch to the next portion of your demonstration, couldn't you simply inject a demonstration by putting the state transition in the replay buffer and training the policy using the same cost function that you used in your trajectory optimization problem?
So I think you're talking about something similar to AMP, adversarial motion priors, where they use a buffer where they include multiple demonstrations and they use the state transitions and they train a network that tries to generate behaviors that resemble the data set. This is one way of doing that, yeah. But in my case, I don't use multiple demonstrations. This is just with single demonstrations now. So I'm just trying to robustly track a single nominal demonstration. But if you want to do it with multiple trajectories, then this is one way to do it, yes.
I mean, you could just train by imitation. So with supervised learning, your policy to imitate your demonstration, and then add robustness by training more with domain randomization and using the same reward functions that you used in trajectory optimization.
So the reason you can't use imitation learning here is because the trajectories don't give you actions. You don't have action labels. You just have the reference state. So that's why you need reinforcement learning to get the actions, apply them to the system, and the only way you can try to mimic the trajectories is through a reward that tries to stay close to this reference. So the trajectory optimization does not give us desired joint positions. It just gives us contact forces and joint velocities.
But can't you recover the desired joint positions from that?
I mean, the trajectory relies on centroidal dynamics, right? So.
Oh, because it's just centroidal.
Yeah, it's not the full dynamics.
Got it.
Yeah.
Thanks.
Yeah, sure.
All right.
So my question is, and I hope that I didn't lose this information, is more about how difficult it is to enable also locomotion abilities with the end effectors or with the arm. Because as far as understood, the legs are used for locomotion, the arm is used for manipulation. Mm-hmm. But can it be enabled any locomotion ability with the arm as well? I mean, I know we're falling into the locomanipulation part, which means basically the same thing, but...
You mean like using, for example, the end effector to grasp like a stair handle and then...
Yeah, also as a fifth leg in that sense.
I think you can extend this to solve such tasks, but then you would need to change the rules that are introduced for pruning the branches. So then this would be different, because now the rules that I introduce, I assume a certain domain that I'm trying to work within, right? In terms of manipulating large objects where you have object affordances defined as prehensile points or non-prehensile points. So you would need to change a bit in the formulation, but I don't see a reason why you can't extend it to...
Okay, because it's something really typical for humanoids. Maybe they're leaning on the wall while making a huge gap, a huge step. Mm-hmm. I was guessing if this can be something interesting also for quadrupeds, and so this came in my mind.
I think this could be extended for this, for sure.
Okay. Are there any other questions? I have a small question. Mm-hmm. So this contact schedule that you do offline, so are you planning to put it online, basically to change it? Because right now the sequence of contacts is the same, right? Mm-hmm. It doesn't change. And if you're doing it online, will it take a lot of time? What's the...
Yeah, that's a good point. So one extension could be to try to make this planner faster, so real time, and then you could update the manipulation schedule as well, right? So now, for example, so now with this structure, if you're using the whole body MPC planner with the whole body controller, you get the reference with a fixed contact schedule, and the MPC planner could adapt the continuous part of the trajectory, right? Mm-hmm. But to update the mode schedules as well, you would need to replan with the actual multi-contact planner. This runs now in around 1 minute, so you need it to be much faster. Yeah, I mean, it depends on the task, but some tasks take like 3 seconds, some tasks take 50 seconds. So you would need to make it faster. But instead, I chose to take the Orel way, which allows you to adapt this context schedule online. Yeah.
Absolutely, it makes sense.